All right, today we are doing chapter 7, which is about atomic structure and periodicity. And we are going to start with a discussion of light. Back in the day, in the early 1900s, they had basically decided that light was waves. And so a couple of things ended up being sort of confusing when they studied them further. We've got this dude here, Max Planck, who has a very nice mustache. And he discovered when he was studying glowing things, like really hot metal and junk like that, that if you looked really, really carefully, you could see that the amount of energy that comes off of a glowing thing comes off in chunks. It's not analog, it's digital. It's like climbing stairs. Like you can be here or here or here, but you can't just be anywhere in there. And that was sort of weird. So he thought about that for a while, and even though they had pretty good evidence that light had a lot of wave-like properties, he said, well, but if light is traveling in waves, why does it come in chunks? And he named the chunks quanta. One of them is a quantum. And so Planck's conclusion was that light has a dual nature. It behaves as waves, and it can also behave as photons, and it depends on kind of the situation that you put the light in as to which one it's going to exhibit, what kind of properties it's going to exhibit. So you've got these two waves here, for example. You need to be familiar with the concept of wavelength and frequency. A wavelength is like, it's not just from top to bottom, it's got to be all the way, a whole wave. So typically that's from, say, this middle here, all the way up and all the way down and to the middle again. That's one wave. So from here to here is your wavelength. Versus on this one, say starting in the middle, you go middle, down, up, middle. That is a longer wavelength. You've got to compare wavelength to frequency, which is how frequently does a whole wave come by. And so you're kind of going one wave, two waves, three waves, four waves, five waves, or one wave, two waves, three waves. So if you've got a short wavelength and you're going your waves come by frequently, so you've got a small wavelength but a high frequency. And if you have a long wavelength, they come by infrequently, so you have to go one, two. So a large wavelength is a small frequency. They're sort of inverse to each other. That is important to know. All right, so Planck, dual nature of light. I have always learned that frequency is represented by the letter F. They keep using V, which I think is dumb. It's not frequency. Also, V is velocity, which is sort of confusing, so I'm unhappy with the use of the letter V to represent frequency. They do that in the book. They may also do it on the formula sheet, but I just don't care for it. I'm going to use F. Okay? So, what Planck did mathematically was he made this formula here, which is E equals HF, not V. The energy of some of the light that's coming off of those glowing things is the frequency of the light times Planck's constant. It can only be multiples of that, so you might have one of them or two of them or three of them, but not anything in between. Planck's constant is a constant, That's h. And its value, which you're going to end up memorizing accidentally, and you probably should anyway, is 6.6 e to the negative 34th joule seconds. And that goes in for h. So the energy that you end up getting is joule seconds, and then the unit for frequency is 1/seconds. So your energy comes out in joules. This formula here is a kind of a substitution of E equals HF, and I need to show you where it comes from. So what we've got is C equals lambda F, where C is the speed of light in a vacuum, which the value is 3e8 meters per second. The wavelength is some value given in meters, and the frequency is some value given in seconds to the negative first, which is also called, by the way, hertz. This is kind of your basic formula for an electromagnetic wave. Wavelength and frequency times gives you the speed of light in a vacuum. It does not work if it's in air or in water or in glass or whatever. Okay, back to the other one. So we've got this one, which is that substituted formula, E equals H C over lambda. That will also work depending on what they give you in the problem that you get. So after Planck, we've got Einstein. Hi, Einstein. He has also got a good mustache, but he's got crazier hair. So Einstein was famous mostly for the special theory of relativity, which is that E equals mc squared, which says that energy has got mass. But the thing that he contributed to our discussion of waves and particles was that he worked on something called the photoelectric effect, which is if you shine light on a shiny piece of metal, depending on the frequency of the light, you can make the metal shoot electrons off, which they thought was pretty cool back then, and they couldn't quite figure out why it did that, and they also couldn't figure out why certain energy photons would do it, but other ones wouldn't, and it depended on the metal. And so he worked out that the reason that it was doing that is because there's a certain amount of energy that's keeping the electrons attached to the metal. If you can strike them with a photon that has got more energy than that, it will knock the electron off. And doing that actually makes a stream of electricity. And so this is a way that you can get electricity from shining light on stuff. So he won the Nobel Prize for that, not so much this stuff. Everyone was like, wow, the photoelectric effect finally explained. So, woo, Einstein. So Planck and Einstein were working on this thing that was, dude, light, which we always had thought was only wave-like, is also particle-like. Crazy, right? Then this guy, he's French, he has a tiny mustache. His name is Louis de Broglie. He is French. You can tell. He was thinking, well, if light, which is supposed to just be wave-like, is also particle-like, what about particles? Can they be wave-like? And he's apparently a smarty because they can be. Because what they found was that one thing that we knew that waves can do is that they will diffract, which means that if you shoot them at something at a really small slit, they will interfere with each other and make an interference pattern on the little detector behind the slit. And so one of the tests that they did to see if particles had wave-like properties was they shot electrons through a slit, and they're particles, right? But they diffracted, and they're like, dude, they're also waves. That's crazy. So that means that not only are light waves sometimes like particles, but that particles also act like waves. So he figured out that if electrons are diffracting, therefore they have a wavelength, therefore they are waves. So his formula, de Broglie, is that your wavelength of your particle is equal to Planck's constant, which we remember, right? We remember that? There it is. Whee! Divided by the mass of the particle times its velocity. Here is a legitimate use of the letter v. What this means is that the particles only exhibit wave-like behavior if they are moving, which electrons have a tendency to do. And mass times velocity is actually a quantity which is your momentum. So it's basically Planck's constant over the momentum of the particle, and that's going to be relevant later when we get to Heisenberg. So this should totally blow your mind, because the diffraction proves that you've got waves, whereas the fact that they're quantized proves that it's particles, and it's both at the same time, and it's terrible. Thanks a lot, de Broglie. So next, we need to talk about Bohr. Something else that scientists back in the day, in like the early 1900s, were wondering about, besides glowing things and how does that thing that Einstein figured out work, was emission spectra, because they had observed them and thought they were kind of cool, but had absolutely no idea why when you made hydrogen glow, it gave off a purple, a blue, a green, and a red line. Isn't that nice?
Yes.
Why does it do that? And Bohr was thinking about, why does it do that? And Planck's idea of quanta, where you've only got specific allowed energies. And he was like, okay, so these, let's say these are specific allowed energies. Okay, so what he was thinking about was Rutherford's model of the atom, where the electrons are kind of zooming around randomly around the nucleus. He was like, that doesn't explain a couple of things, like why aren't they just falling into the nucleus? Because electrons are negative and the nucleus is positive. Like, they should go and get together and be happy. But they're obviously not. They're going around. It's kind of weird. But if you think about it in terms of Planck's, there's only specific places that you're allowed to be. Well, then you're not going to slowly spiral in, boonk. You're going to stay where you're, like, permitted. So that's where he came up with the concept of an orbit that had a specific radius, and they were a lot more organized. Rutherford's just had them kind of going in orbits around the nucleus. So he came up with circular orbits that had a specific radius, because that kind of solved the, well, then why isn't it falling into the nucleus? His answer is, because they're not allowed to. Okay, it sort of solved it, but then why isn't it allowed to? Shh, we'll answer that later. He also kind of used that to work out what the heck the deal was with the emission spectrum, which is that in the ground state, that's when your electron is at the lowest energy that it's allowed to have. That's the closest orbit to the nucleus. You can excite those electrons by striking them with photons, and now you've given that electron more energy, and so it goes wee plunk and pops up to another level, another orbit around the nucleus. That's the excited state. And what he sort of postulated was you shoot it with a photon to pop it up, and when it pops down, it shoots out a photon. Well, it's a specific amount of energy between the orbits, and the photon that it pops out is the amount of energy between the big orbit and the small orbit. And the amount of energy between the big orbit and the small orbit is a specific wave, which is a color. And it turns out that actually hydrogen has got a bunch of emission lines that are not in the visible spectrum, but it turns out that those are invisible, and so they didn't see them until later. He worked out this whole thing and did all this crazy math and figured out exactly where all the orbits were. Like, this is n equals 1 and n equals 2 and n equals 3, and if you hop down from 5 to 1 you get this color, and if you hop down from 4 to 2 you get this color, and worked it all out, and it was fabulous, and everyone thought he was a genius. And it works on hydrogen. But if you have more than one electron, it doesn't work at all. And so he was really smart, and he did a really good job with this, but it's not actually true. But we did gain a lot of insights from him, because it is true that you've got electrons going around the nucleus in specific allowed states. They're not circles. And you do have the ground state and the excited state, where you can be low energy and high energy, and you pop up and down and release a photon of a specific color. It's not circles. Okay, well, now we get into crazy elements. Come here. Called polyelectronic atoms, which is atoms with more than one electron. And the question that you get is, well, then why is hydrogen so good, but all of the other elements are confusing and don't work with his model? And the problem that you encounter is that when you've got several electrons near each other, they interact with each other as well as with the nucleus, and so it's not as pretty anymore. So they're pulling on each other, and they start shielding each other from the amount of charge from the nucleus, and so that's why it doesn't work as well. And what ends up not working as well is that all of the different shapes for hydrogen, like when you get into the SPDF quantum model, they're the same energy. So like 2s and 2p, those are the same energy. It's called degenerate. It makes them sound like they're like got bad morals or something, but it means they have the same energy. But when you get to polyelectronic atoms, the 2p is just slightly higher and the 2s is slightly lower because of all of the interactions and neener. So that is where we get to here. So after Bohr's model of the atom, you end up with the quantum mechanical model of the atom. And in the quantum mechanical model, we solve one of the problems that Bohr had, which was when you ask, well, why don't the electrons fall into the nucleus? His answer was, because they're not allowed to. Sort of begging the question. The reason is because the electrons are acting like waves, not like particles. Thanks, de Broglie. So they're not little particles that go because if they were, they would be following kind of classical physics. But instead they're doing this crazy quantum mechanical junk where they act like waves, and then every now and then they act like particles when they feel like it. So because they are waving around the nucleus, they don't fall in with a predictable orbit kind of thing. Dude face Heisenberg here did a whole bunch of math and figured out the orbitals. It's important to remember that Bohr did orbits, which are little circles, and the orbitals are the probability maps of where the electrons can be. And you end up seeing those kind of things that show you the shape of where the electron probably is. Its probability that's mostly around here in the center when you're talking about, say, an S, but it can be out here, but pretty infrequently. That has to do with the Heisenberg uncertainty principle, which is you can't know both the position and the velocity of a particle perfectly at the same time. And that comes from this formula here, where you can know the momentum, but you can't know both you can't know the position and the velocity. So that the more you know one of them, the less you know of the other one. And so it's kind of a balance. So you don't end up with a really clear answer to what is that electron doing right now? You can't really answer that question, but what you can do is say, in general, this is the sort of thing that these electrons do. They kind of stay in this shape B area. And that is what an orbital is. You don't have the pretty circular orbits like Bohr said. What's cool about orbitals is that they actually stretch like to infinity. So there is a very, very, very small likelihood that like one of your electrons is over there right now. Or like in Chicago or across the universe. Whoa. It's really small. It's very unlikely, and it's probably never happened because of how small the likelihood is. But that's why my superpower, were I to ever be given a superpower, would be to affect probability, because then I could teleport anywhere I wanted to. Anyway, so the orbitals stretch to infinity, and the problem with having a volume that stretches to infinity is that it's kind of hard to draw that shape. And so they kind of settled science decided, okay, look, we're not going to draw the infinitely large shapes. We're just going to go at 90% probability. We're going to draw a line around that area. That's the orbital. But it can be outside of it. Just generally it isn't. So that's your orbital. And now we've got descriptions of orbitals, which are described with exciting letters called quantum numbers. Scroll up a little. Yeah, okay. Quantum numbers. One thing that you need to remember about electrons in atoms and what their deal is that each electron around the atom is unique. You can only have 2 electrons in each orbital. One of them spins one direction, one of them spins the other direction. The orbital is full after you get 2 in there. That principle is called the Pauli exclusion principle. So here we go, quantum numbers. N actually comes from Bohr. He was the dude that came up with N because he was talking about the circles, and he would say, you know, the first orbit is n equals 1, the second orbit is n equals 2, the third orbit is n. They kind of stole that from him, and they said, all right, your basic like amount of energy and kind of your basic radius, we're going to call that n. The close ones are 1, the slightly farther ones are 2, the slightly farther ones are 3, 4, 5. So that's n. So when you have n equals 1, it's low energy and small. N equals 2, it's slightly bigger, etc. That's called your principal quantum number. And if you have a electron configuration where you run into something like 3s2, n is the 3. If you've got 2 different orbitals and they have got the same n, like 3s and 3p, they have similar amounts of energy. They are degenerate in hydrogen only. That's why I said similar. In hydrogen, 3s and 3p, they have the same amount of energy, but when you get into bigger atoms, they are funkified, and so you're slightly different. And so that's your n. L is called your angular momentum quantum number, which is the orbital shape. You're probably more familiar with sp, d, and f. Because they decided it had to be numbers, they decided it had to be numbers. So s is 0, p is 1, d is 2, f is 3. Why didn't they start with 1? I don't know, they're retarded. You can also get bigger than f if you have an excited electron. And these shapes are even crazier than f shapes. And I've seen them somewhere. They're like quadruply crazy, three-dimensional flower craziness. And you run into G when you excite an electron really high. So that's your shapes, 0, 1, 2, 3, SPDF. Your next one is M sub L, which is your magnetic quantum number. This is your orientation, and what they're talking about is magnetic in terms of, like, think of a compass. Is the orbital oriented on the y-axis or the x-axis or the z-axis? If you've got an s orbital, it's a sphere. You can't really orient that. Like, go ahead, try spinning a sphere, see where you get. So they only have one orientation, and so the number, because they demanded numbers, for S, when you get to this third quantum number, is always 0. Again, the people that came up with these like zeros, so they set the normal, like the middle one, at 0. So that's S's. If you've got p orbitals, there are 3 p orbitals. You can have a p orbital in the x-axis, you can have a p orbital in the y-axis, and a p orbital in the z-axis. Those are numbered with 0 in the middle, and then the left one is -1 and the right one is 1. Again, why isn't it 1, 2, 3? What can you do? D's are flowers. You can have a flower facing up. You can have a flower that's canted a little bit. You can have a flower that's flat. You can have a flower that's rotated. And also there's a donut. So these are called x squared, y squared, xy, x squared minus y squared, and z squared, which is pretty rough. You don't have to know that. But that's just kind of referring to, like, well, it's in this axis kind of twice, and this axis. So your quantum numbers for that are, the middle one is 0, -1 and -2, and then 1 and 2. F's are double flowers. You've got a couple of double donuts. You've got 7 options, which are, maybe we have 3 double donuts? The middle one is 0, it goes down to -3, it goes up to 3. I don't know, it makes a nice pyramid, don't you think? So that's ML. And then MS is your spin number, which is either up or down, which is +1/2 or -1/2. That's an obvious number to describe up and down, don't you think?
Yes.
I've always thought so. All right, so you just kind of need to know that stuff. And now we have some problems to do. So this is your chance to pause the recording and go and do these problems yourself. And then if you have any trouble or whatever, you can come and see how I did them and see if you're right. All right, give me my white pen. That's not white, it's blue. All right. What is the frequency of light having a wavelength of 4.50 e -6 centimeters? All right, that's going to be a problem that involves frequency and wavelength, which is this equation up here that I showed you a little while ago, which is the speed of light is equal to wavelength times frequency. And we know this is a constant, which is 3e8. And our wavelength is 4.50 e -. Ooh, no, it's not. Better undo a couple of those. Because centimeters doesn't work. Because 3e8 is in meters per second. So that means we need to convert centimeters to meters, which is swoop swoop. So that's going to be e to the -4. That's a 4, okay? 4.
Okay.
Times frequency. So frequency ends up equaling, type. I already did these. 1.5 e to the -12 seconds to the -1st, also known as What are you doing? Why are you doing that? Don't. Stop. Stop.
Oh my gosh, your computer just went crazy.
Can I have my pen back? Did you see that, people? It's a ghost. Gonna put a mark through that because it's crazy. And that's gonna be 1 point. Don't start that. 1.5 e to the negative 12th seconds, also known as hertz. All right, question 2. When a boron compound is heated in a flame, light with an energy of 3.85 e negative 19 joules per quantum is emitted. Using the diagram below, what color will be observed in the flame? So what we have is energy, and what we need is frequency. And so we're going to need our formula that involves energy and frequency, which is E equals HF. Our energy is 3.8 e to the negative 19. Our H is Planck's constant, which is 6.6. 6.6 e to the negative 34. And our frequency we don't know, so we solve for frequency, and it gives us, what does it give us? 5.75 e to the 14th seconds to the negative first, also known as hertz, which is going to be right in between 5 and 6, kind of 3/4 over, which is green. All right, question 3. Which of the following energy levels are not allowed? This is basically asking you to remember what the normal dudes are for electron configuration. So that's 1s2, 2s2, 2p6. And if you remember this kind of shorthand way of doing the list of them, it will go well with you. Do you remember doing this? I don't know if I showed you this. This is kind of a short way of remembering the list without having to stare at the periodic table forever. You go 1s to, it's actually 7. And then F starts at 4. Now starting here, these are excited energy levels, 6F, 7F, and actually you can have G's, in case you were wondering, starting at 5. Uh-oh, don't erase my stuff. It's going to do it, isn't it? So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6, 7s2, 5f14, 6d10, 7p6, and 7d10. And that gets you down to unu noctium. So all these dudes are excited. But which one is not allowed? Turns out that basically anything bigger is allowed, but that smaller ones are not. So, for example, 3D. 3D exists. There is no 2D. Nope. 1s exists, 5p exists. 3f, though, does not exist. F's start at level 4. So, boop. That's your correct answer, and 6s, it does exist. And it is allowed. All right, and then the maximum number of electrons that can exist in the n equals 4 energy level is, well, n equals 4 is going to involve some 4s, some 4p, some 4d, and some 4f. There's no 4G, because G's start at 5. So the number of electrons that we can have is, in an S you can have 2, in a P you can have 6, in a D you can have 10, in an F you can have 14, and that is 32. Bam. Is that... Oh wait, no, there's more problems than that. Okay, and question 5. The outermost electron in the ground state indium atom is described by what set of quantum numbers? Well, we gotta go find indium. Hey, periodic table. Indium is number 49. Hello, indium. Right here. This is in the P block. It is in the 5p row. So the last electron in indium is going to be 5p. 5p. And because you're just starting 5p, it's that one. Hello. So 5, you've got n equals 5. That's your principal quantum number. You've got L is defined by P, which when you remember the numbers for them, it goes SPDF 01, 2, 3, so L is 1. M sub L. This is the stupid one that has 0 in the middle, so this is 0, -1, and 1, so that's -1. And then the last question is, what is your spin? Is it the up dude or the down dude? This is the up dude, so that's +1/2. So that is your 4 quantum numbers. Bing! Alright, and number 6. What is the electron configuration for an atom of nickel in which one of its valence electrons has been struck by a photon and excited to a 5G orbital? We gotta find nickel. Nickel! Here's nickel, number 28, which is, let's see, stopping at 3D8. So let's go all the way there. So that's 1s2, 2s2, 2p6, 3s2, 4, what? 3p, yes, 3p6, 4s2, 3d8, except one of its valence electrons has been struck. Which one is the valence electron? Well, the valence electrons are the ones that are the biggest, so it's the one with the largest n. One of our valence electrons is in here. So this guy, one of these two has been struck. So he's gone now. He's 4s1. And that excited electron has now become what kind? A 5G. 5G1. So that looks like a 10, but it's not. It's a 1. That is the electron configuration of an excited nickel atom. The end.